force eventually start to be useful, right? You already know that, oh, what is segmentation force? And why we suddenly have to segmentation force, or why dereferencing a null pointer has segmentation force. Okay? So why? Because the null is equal to 0. You dereference it, it goes to this range, the unusable range. Sorry, segmentation force. Okay? So you can try. Maybe you don't dereference null pointer. Dereference pointer value equal to 1. You can still get segmentation force because it's still inside this range. Okay? So what's next? Next, I give you a very horrible program. I think this program you need 2 minutes in order to understand what I'm doing. Very horrible. The trick is to make use of segmentation force to measure something. I'm using segmentation force to measure a thing. What is the thing that I want to measure? Take a look. Oh, by the way, do you know what this statement means? I point to the start of the main. Oh, I already have. Oh. Do you know why I do it? First of all, when the program stops, will the program stop? And when it stops, okay, why it stopped? I would say that is an effective use of segmentation force. Yes, then? Yes, that's right. Any idea? Let me run the code first. Okay, what? C variable. Oh, no, it determined that I never use it. Okay, thank you. So let's run it. Will it stop? It will stop. It will stop. Okay, so already there is an answer. How about others? Do you know why it stopped? It's because of segmentation force. Okay, I eventually drive the program to reach a state that it was segmentation force. And because I handle segmentation faults, okay, can you see that I handle segmentation fault? I use signal to state that if you have segmentation fault, don't stop the program yet. Go to my handler, okay? And inside the handler, I do some conversion, okay? So what exactly I'm doing is, let me go back to the map, okay? What exactly I'm doing is I have a pointer pointing to this green location. And this pointer will eventually decrement. And it will walk in this direction until it touches this red line. What will happen next? If I touch this red line, I will go into the unusable zone, segmentation force. Okay? Then I can measure exactly where this location is. Now, I give you another question. Can I measure this line? The boundary between the code and the global. How can I measure this? Can we use this program to measure this? How to measure the boundary between global and the code? I just need some steps, okay? I don't want a complete story here. Now here the step is, for this program, I point to the code and keep reading the code. But after I read one byte, I go down one byte until I touch the bottom boundary and then submit the fault. How about I want another side? Any idea? No? No idea? Very simple. Here, what should I change? Change your an address in global. Right? Then how about here? Change from read to write. Then I can measure this. Why? Yeah? Yeah, you cannot write address in the code. Okay? So you keep on writing your global variable. Okay? And suddenly you will touch. Wait. You will touch this. Wait. Why always me? I already changed the battery before the start of the lecture. Yeah, suddenly works. So that means I will keep modifying, but I'm afraid that maybe the program is not perfect. So why the program is not perfect? Because I used global variable to store my pointer. Maybe so happen that I modify my global variable and drive the program crazy. So in that case, you need to use malloc. It's just malloc to help to create the pointer. Okay, so that while you're doing the modification over the global variable, it won't modify yourself. Okay? So, where can I find this program? This program is found. Before I found this program, I already have this idea. And so happened that I found this program in a book called. No. It's called Binary Hack. Where is the book? Why? Book. This one. Binary Hack. In Japanese. I don't know Japanese. Okay? So I find some translation version. Okay? So this is Binary Hack. Okay? So this is summary about the entire user space memory. Okay? And entire user space memory, the most useful part is why you get segmentation fault. Now you understand this. Maybe you get segmentation fault, you're too conservative with malloc. Okay? You malloc too small area, and you try to use beyond that segmentation fault. Right? And now you know why. When you free, you get segmentation fault. Yeah? Anybody try this? I already heard some of the people while doing assignment 1 tell me that, can I not free my memory? When I free my memory, I get segmentation fault. Okay? Now you know why. Because inside the malloc, when you call free, it's trying to manipulate the free list, but you corrupt the free list. Okay? Then when you corrupt the free list, when you try to expand the list, it's failed as segmentation fault. Okay? And it is not your fault. Even you use GDB, the debugger will tell you that the faults come from GNU-C library. Okay? Yeah. A free list what is usually is a pointers and size. The pointers values point to your location inside the game. So if you say, let's say I write now there, I write all the values in the now, then it will form the now pointer and get the fault. Okay? So you basically corrupt it. Now how about this answer? Yeah, some people love to do some argue with me with one point. I always say that you need to be exact in doing malloc. Okay, they disagree. They always say that, yeah, I can manage a fewer memory, okay, and then I can still have my program work perfectly. You are lucky, okay, because after that, okay, you may have other blocks, neighboring blocks for you to override, okay, and sometimes even not because of a malloc, okay, you still go, oh, but why there is no problem? You are lucky. Somehow inside the assembly code, okay, not malloc, it creates a bigger array than you can imagine, okay. So this is a map in measuring how lucky you are, okay. So what is the meaning of measuring how lucky you are? We have a read-only segments, okay. You read it, no problem. But write this 724. Allocated segment, now depends on how many memory you have allocated. Okay, if you allocate more, you will have less chance to get 724. You have fewer, bigger danger. Okay, so here, of course, no matter read and write, you will get 724 in an unallocated area. Okay, that's it. Any questions? No questions, huh? Wow, cool. Okay, I can finally, okay. I already didn't teach about part 2 for at least 2 years. This year I have time now because I cut many of the details, so I have time. Okay, part 2. I mean, the part 2 is the part that now. Right? Why cannot this? Okay. Part two. Okay. Well, why click this? Open it in the browser. Okay. Good. So although I write here up to page 51, it actually depends on what is the progress during the time I am in a mega class. Okay. If I'm good in the progress, then we will follow this. If I'm not good in the progress, before the start of the examination, I will tell you which questions that is going to be cancelled. Okay? So I will cancel some of the questions if I'm bad in the progress. Part 2, part 2 is a very valuable thing because this part is to tell you how modern CPU understand the process. And the story starts with a very horrible program. Okay? And what is the big story inside this part? The big story inside this part is I again try to wipe out all the things that you learned before. What are the things I want to wipe out? First of all, the CPU and the memory. What's the relationship? Relationship is you put memory into CPU and run. Right? And this is what you get. But I will tell you that no. The writing and reading are not so direct. Okay? And also it seems that the CPU and memory, there is some communication, right? If you already understand some hardware things, you know that there is a memory controller inside the main board to ship data from here to here. What is their relationship? Huh? And there is a very funny relationship between it. And this triangle are the 3 main topics that I will talk about, but I don't say there's topic 1, topic 2, topic 3. I will start with a very horrible program in explaining the entire part. This is a horrible program. So what is this program? The program is very simple. You already know fork, right? I call fork, okay? And after fork, I print my PID, no problem. Now, what is more is I not just print my PID. I also print the variable that stores the PID return value. Okay? The address, I will print it out. And what is the result? Now, this is something that you may not accept it. Good. I call this program called same address. What is the dilemma here? What is something contradicting? The contradicting thing is I have 2 processes. They are different. And they report to you that they use the same variable, right? Because they are from the same program. And the same variable is called PID. And, oh, by the way, I didn't cheat, okay? Yeah, I didn't cheat, okay? They use the same variable. They carry different values in the variable, right? Because they are using fork. They should one carry 0, one carry non-zero, but their address is the same. So what is the contradicting fact here is something really not in your brain even define what is a memory address, and all the things that people tell you that memory address is to represent a variable. Now what I'm telling you here with this program is telling you that a piece of memory can store 2 values. Right? No, of course not. Can I have one variable called 2 values? Yeah, right? Unless we have a quantum computer. The quantum computer can store many variables here. Do you know that? Yeah. Quantum variables and quantum bits is they're oscillating, okay? I mean, not oscillating. Unless you see it, okay, then it won't be fixed. Very interesting. Yeah, don't care about it, okay? So, yeah, unless you're from physics. Then why is that, okay? I really, the first time that I see this while I was 15 years ago, I don't understand, right? So I flipped some books because, but that time the one who teach me OS don't show this program, okay? And now I show you this program, I have the responsibility to tell you why, okay? Because if I don't tell you why, you cannot proceed in using C anymore, right? Because I'm telling you that C is a very special language. Huh? Depends on how many forks you are using, and that variable contains many values. No, it's not the case. The case is the story starts with this figure. Okay, the big story starts with this figure, and this figure, I know about this figure in my year 1 course, ENGG 2020. But I know in your curriculum, ENGG 2020 never talk about this, right? Did you see this before? No. Yeah, I know that. Okay, so that means that I need to take the job of ENGG 2020. Okay, so what is this figure? This figure is very easy to understand, right? Here, I represent the memory. I represent the memory here. I represent the CPU here. And CPU has a variable called, not variable, register, called program counter to point to the code that I need to execute. Okay? So the cycle of execution is what we call fetch, decode, and execute. I fetch a piece of instruction. Let's say there is an instruction here. So step 1 is copy that instruction from the memory, put it in the CPU, not run it immediately. Okay? Just try to copy that, put it in the CPU. Oh, be careful. Okay, I know you're sleepy. Okay. So put it here. Decode. Next step means that I will need to understand what this instruction is talking about. And this this instruction may be telling you to do things like load and other variables into the CPU. So it may go to the RAM again. Following, let's say, I go to this location, 0x12, which has decimal, 1, 2, 3, 4, 5, 6, 7, 8, to get another memory and put it in the CPU to run. Okay? If you follow this diagram, we cannot explain this. Right? We understand that, okay, what is the meaning of loading a memory? Okay, using memory address. Load that memory from the physical RAM, put it in the CPU. Now I can explain anything. Because these two processes telling me that they use the same address. If it's follow the same address, load in from the RAM, that means that I have 2 pieces of RAM. No, I only have 1 piece, okay? So 1 piece of RAM, how to give you a different views, okay? Now this is the CPU design since Intel X03XX. 3XX is the first commercial, commodity. Commodity means that every people can own, okay? Cheap CPU, okay? First batch of cheap CPU that support this kind of thing to allow two processors, okay, using the same address, but the same address give you two different values. And the trick is insert one thing called MMU, Memory Management Unit. Okay, it is not any controller. It's not hardware controller on your motherboard. It is hidden inside your CPU. In the CPU, there's a component. So that's why I put a box here for MMU. And MMU is very interesting. The MMU will change the fetch, decode, execute cycle. Okay. Now, what this MMU is doing? Let's say the program counter is storing this address ABCDEF00. Okay? And this is what the CPU think I need to get. I need to get this address so that I know what is the next instruction I should run. Now the MMU job is to translate this address. Where this address is coming from? It's coming from program. The program say that I need this, but the memory management unit think that it's not. I will do a translation, translate into another address, and this address before translation, we call it virtual address. After I translate it, we call it physical address. Yes? Virtual address. And usually, virtual address is an address that you can see using printf, printf%p. And that address is called virtual address. Okay? Yes, every address that you can print is virtual address. You can never see physical address. Physical address translation is hidden inside the CPU. Okay? And the CPU will do the translation for you so that you can see another address, and that is the true place that your process using that piece of address. So what is the meaning? The meaning is for different processors, they hold the same virtual address. But this MMU is clever. They know that you are CPU, you are process 1, you are process 2. I do two different translations for you, so that you will be guided to two different physical address. And this is how modern CPU support multiple processors switching, and I switch from one processor to another. It still know where to find your memory. Okay? And this translation will go on. Here is the physical address. And after this, maybe I need to do another job. Let's say I want to load an address 1234, 567X. Then it will translate into another physical address. So this translation happens endlessly. Whenever the program or the process loading some new address in, the process will load virtual address into the CPU. CPU know about this, ask the MMU for help to do the translation. So this is a separate world. In the memory world, we work with physical address. Inside CPU, we have virtual address. So that's why when you print something, the print address is always virtual. And the translation is using a new unit inside the CPU MMU. Okay? So this is the hardware design. And it's changed the entire story. And the story is telling you that different processes basically will have different allocation over physical address range. Okay? Maybe you own the first part, not first part, maybe you have 4 pieces of RAM, okay? Let's say you are running your favorite game, or LOL, lead memory, okay? I allocate all things into the first memory chips, the first memory slot. Then you can still run another process. They may use the same set of virtual memory, but it maps to the second piece of memory, and so on and so forth. Okay? And the trick is done by this hardware called MMU. Okay? So with the help, we can get the target like this. Okay? So this is the modern CPU design. 2 different processors, let's say process X and process Y, although they use the same set of virtual memory, they may map to different physical address. And this is the trick. Any problem? Easier. This is a mapping. So that means the previous fork program BS program. Now we can explain what exactly happening inside the fork. When you do fork, basically the system will create another piece of physical memory for you. They point to two different physical memory. And although you call for the address of PID, you are using two different processes, so I go to two different physical locations. Although you print out, the printout is something identical, the printout is just virtual. Virtual and physical. And by using this, okay, basically we can support many features that you now enjoy. First features, many processes run together. Second features, I have many processes run together, and I can scatter the memory into different memory location, including the hard disk. Right? I can put something on the hard disk, okay? During the translation, MMU suddenly find that, oh, it is not in the physical memory. Then I crawl it from the hard disk back to the physical memory. Okay? We can scatter the storage location to whatever place you need. Okay? Maybe you can even dedicate an SSD for that. No problem. Okay? Yeah, but don't do it, okay? You're wasting your money. Okay? So this is translation. So how to implement it? To implement it, okay, we will bring forward one important name, okay, in the computer world called paging. This is just a name, okay? And the name is to tell you that the location of each piece of memory, okay, while we're doing translation, okay, is not depending on a particular address. So what exactly it is doing? Let's go. And I give you the motivation first. The motivation is this. Let's say, how to implement MMU, right? MMU do translation. And this is per process translation. So whenever you switch a new process, the MMU need to adopt to it. Okay? So the easiest way is to implement a, I don't know what is your idea, maybe a hash table or maybe something like that. Let's say I use the dumbest method of all. I use an array, lookup table. Okay? And you can use hash table or use a binary tree, binary search tree, a web tree, whatever things you can think of in indexing all the things. But I choose to have an array. Okay? So that you understand what I'm talking about. Let's say this is an array. Okay? I will use an array. You give me a virtual address. Okay? Give me a virtual address and map to a physical address. No problem, right? What is the storage requirement here? How many memory I need to come up with this big table? Hundreds? What? Size. I mean size. Now, the number is huge. I will do it like this. How can I come up with 16G in storage this guy? Okay, now I do it step by step. Very easy. I know that this is an array, okay? And I will map every virtual address to a physical address. Okay? Do I need to store the virtual address? Basically, we don't need to. Because the virtual address is continuous, starting from 0 all the way to, what is the value? I cover it, sorry. All the way to here. Okay? So basically, it is a array index, right? This is array index. So when you create an array, do you need to spend some space for the address of the array? No, you don't need to, right? So I don't need to store this column. I don't need to store this column. And I know that the first entry will be mapping the address 0, so on and so forth. Now, what is the size of each address? If it's 32-bit CPU, 4 bytes. Okay, I need 4 bytes to store each address. And how many addresses I have? Okay, although I know that, oh, I don't need to store 0. That 0 is useless. Whenever you want to translate 0, I don't need to do any translation. Immediately give us an encryption false. Okay, but still we do a worst case scenario analysis. The worst case is I have so many addresses here, 2 to the power 32 times 4. So this is 16G. Okay? Do you believe that your CPU has 16G? If your CPU has 16G, why you need memory? You don't need to buy any memory, right? So this is not the way, right? I cannot do a lookup table like this, okay? I don't know whether you have come up with any clever means. Let's say you use hash table. You still need so many memory, right? I don't know whether you want to build a tree. Or build a tree is crazy, right? You need 2 more 4 byte pointers. So the memory usage is much more, okay? None of the any practice I mentioned just now works in this case. So the CPU designer are very clever. They change the game totally. Their way to change the game is don't translate address to address. Don't do a translation address to address, but block to a block. What is the meaning? What is the meaning of block to block? Okay? So maybe if you have taken some of the courses, I already heard of people saying that in it's A-level curriculum, it taught about this map already. Okay? And some other schools like IB or HiDib or Associated, we may have taught about this. But you may not heard about why we need it. Why we need it? Because we don't want to have a byte-by-byte translation. We want to have block-by-block translation so that we will break the virtual address into 2 parts. What is the meaning? The meaning is I will only translate 20 bits, the most significant 20 bits. Don't translate all 32 bits. Only translate this part and make it into a new physical address. So how about the last 12 bits? I don't translate. I just don't translate it. So with this control, what is the end up effect? What is the end up effect? Maybe you don't know. You maybe need some picture to help you. I have a picture here, but I first want to do the calculation if I do this translation. Okay, the translation calculation is meaning that how big this lookup table is, how big it is, how many addresses going there. At most, I need to translate all 20 bits. The number of variations will be 2 to the power 20. 2 to the power 20 times how long is an address for a 32-bit CPU. Although I fit in 20 bits, you still need a register to store it, right? You still need an address type to store it. It is a 32 bits for each address type. So 4 times 2 to the power 20 format. Feasible, right? Feasible. Although you know that the old CPU don't have format. Okay? We have other ways to solve this problem. But already there's a reachable goal. Reachable goal from 16G down to format. Yeah. Okay. So what is it? We call this technique paging. This technique is called paging. Okay? And this paging basically translate address in a block-by-block style. What is the meaning of translating block-by-block style? I have a diagram. Okay? So what is this diagram is about? Okay? The diagram is about what is the true meaning of translation. The true meaning of translation is this part, the 12 least significant bits. You don't translate it, right? And when you don't translate it, let's assume that, okay, this is 12 bits. So the starting 12 bits will start from 0, and then 0, 0, 0, 1, and then 2, and not 2, sorry, 1, 0, okay, and 1, 1, all the way down until you have all bits turned on. They are consecutive, right? If it is a virtual, from 0 all the way to all 12 bits turned on, they are consecutive. After translation, they are still consecutive because you never change it. But in my previous example, I translate address to address. You may break the consecutive virtual address into non-consecutive physical address. Now, I won't do it. I will translate consecutive address passing through this big flow chart into consecutive physical address. So that means what? That means basically the translation won't break the neighboring relationship. Won't break it within one area. And what is the area? This area is shown here. The area is per 4096 bytes per disk area, they will be kept consecutive. Why it is a 4K? Because the consecutive numbers of address, okay, is defined here using 12 bits. 2 to the power 12. What is 2 to the power 12? Okay. Yeah, 2 to the power 12. 4096. Okay? So that means I have 4096 addresses. When they are consecutive, after translation they are still consecutive. And it's form a translation block. When I translate, block by block translation basically. Yeah. And that means inside the physical address, what does the physical address become? Physical address will become an array of 4K blocks. And we call this one page. 4096 page. Okay? This for one page. And why I keep mentioning this using around 5 minutes? Because this is the minimal, really minimal allocation of memory for every computer now you're using. No matter you're using iPad, no matter you're using iPhone, no matter you're using laptops, this is the minimal allocation unit. You may not believe in me, but later I have programs. I ballot for 1 byte only. But the system really gives me 1 page because of this. I can try later, but not within this class, but within the makeup class. Okay? Yes. Right. Not MMU is not very cubic. Okay. Yeah. The MMU, the number of pages is huge, so they won't use local table style. They use a tree. Why does it use a tree? Because it can use null pointer to represent that this big area is not allocated. If it is an array, how can you represent a translation fail? Translation fail may be the translation map to null, right? And you need to set up every entries to set up this null translation. And eventually this will fail as in the 64-bit CPU design. In 64-bit CPU design, not just 64-bit CPU, because I said that this emerged starting from 3XX already 20 years ago. 20 years ago, 4 megabyte is a huge number. Okay? So they will just keep a point inside the CPU, not the entire point. And they arrange the entire table into a tree. So that, yeah, I will draw it out. No. And why I say because I have the notes for this design. But you know, if I show this note to design, often design people will treat this up. Oh, do you need me to revise it? Okay, so it uses a tree. Basically, the tree has many edges. If you don't allocate a particular physical memory, it will point to null. And this represents a huge area because down the tree is other levels. With one null pointer, it representing a huge area of unallocated zone instead of using an array. An array cannot provide you this control. An array, you still need the memory to store that null for every translation entries. So this is how CPUs start the paging support. We call it paging support. They start with a tree, not start with a table. I show you a table because table is much more easier to understand. Okay, and you can already look it up. The technique and the storage of this tree is called TLB. Yeah, translation look aside buffer. Okay. Oh, by the way, I go back to here. Okay, so I finished this page. I will stop this lecture. What is the meaning of I said that consecutive translation. The consecutive translation is like this. Let's say I have a virtual address like this. Virtual address starting at 1234500, 1234500, 5001. Now they are consecutive. Consecutive, and here is also consecutive because from 1, 2, 3, 4, 5 FFF, next address is 1, 2, 3, 4, 6, 000. Right? Now, as if I have a consecutive virtual address, but after I do translation, because translation don't translate these 3 guys. Do you know that each guys of it contains 4 bits? Each guys here for 4 bits. 4 times 3 is 12. So this 12 bits won't do translation. So that means that this guy will stay together, and the only thing changed is this guy. So the mapping is whenever I see 1, 2, 3, 4, 5, I map to 5, 4, 3, 2, 1. Now this is not the true case, okay? Don't think that in a true memory, always 1, 2, 3, 4, 5, go to 5, 4, 3, 2, 1. No, okay? So this is the mapping. And now, how about this? This will map into another area. Let's say it is 09394, okay? Or some will say, okay? Then it goes to 2 different locations, but in a block style. And this block, we call it a page. Okay? Paging is interesting. Okay? Because this program, I promise you that I will show you in a makeup class. You can go to your computer, I don't know what kind of computer it is, to run this program. This program will tell you the system page size. Okay? This will tell you the system page size. I don't know what is your CPU using, because some of the new CPU already support huge page. Okay? So let me look it up for you. Let's say Intel i7 TLB size, page size, okay? Page size. It already support here. Wikipedia is faster. Oh, here is also have fails to pick for okay, page size. Yeah, it said it's a standard 4K, but Intel already going to support bigger page. If you're using i7, you may have a chance to support a big page. So before you come to the bigger class, you can go to let's say this guy using Apple, this guy any other people using i7. Apple is not using i7, sorry. If you're using i7, try it. Whether your page size is 4K or 2 or 4 Mac. Okay? Don't try it on your phone. Okay? The phone cannot compile the program. Okay? So that's it. We will have although it's a little bit early, but I know that you cannot take too many stuff. Okay? So I give you a long break. 7:30. We will be in LSK. LT5. I hate that place. Okay? That place is a huge hall, but no people coming. And it becomes a very horrible hall. Okay? That's it.